Okay, linear algebra lecture 12, matrices as functions. So we're going to look about matrix multiplication and think about that as a function. What are the spaces that we're going to be dealing with, and what is how do bases come into this? So here's a matrix. How is this a function on the set of two-dimensional vectors? Well, if V is a vector AB, then M times V is 1, 3, 0, minus 2 times AB. If we multiply this out, 1 times A plus 3 times B, 0 times A minus 2 times B. We call this W. This is also a two-dimensional vector. So multiplication by M takes a 2D vector to a 2D vector, right? So what it takes is its inputs. We generally call that the domain. And then we call the outputs. Technically, we call that the codomain or the range or the image. I'm going to draw a distinction between these words in a little bit. So, and there's a rule. And that's what a function is. You have a rule that takes inputs to outputs, and the rule is well defined. So it takes two-dimensional vectors and turns them into other two-dimensional vectors. And we can think about this geometrically. I start off with a vector like that. This is in my domain. And I multiply it by M, and it ends up over in my codomain. And what's the vector that I get? Well, B is this long thing here. So my x coordinate becomes A plus 3B. So that's A plus 1, 2, 3Bs. And then minus 2B is my y coordinate. So minus 1B minus 2B. This is the vector A plus 3B minus 2B. And this is the vector AB. So this vector here gets turned into that vector there. So what does the matrix do? Matrix multiplication do to this vector? Well, it flipped it over the x-axis and made it longer, and it changed the direction. A little bit hard to figure out what's going on there, but we have tools to make this geometric interpretation a little bit better. So first we'll show that this is linear. Remember that linear means, we've seen this for some of our differential equations. When we're doing Laplace transforms, in fact, Laplace transform is linear. If I have two vectors and I multiply them by constants and add them together, I can calculate this by multiplying with the matrix on each term and then adding them together. But a constant means I can actually multiply the matrix times the vector and then multiply by the constant. So linear, this is what linear means, is that this side equals that side. Okay, so how do we use the basis ij of two-dimensional vectors to explain example 1? Well, if I start with a vector AB, I can break that into two vectors. And then I can factor out that A out of the first one and factor that B out of the second one And remember that we have names for those particular vectors, I and j. This one is I, this one is j. So what's m times AB? Well, m times AB is m times a, which is now we're thinking of as just a number, times the vector I, plus b times the vector j. So it's a m times I plus b m times j. Which is an interesting thing here, right? This is a vector, this is a vector, and what we're saying is that the vector AB gets mapped to another vector with coefficient a and b, so the coefficients stay the same, it's just the vectors change to m times I and m times j. Now, m was the vector 1, 3, 0, minus 2. So m times I is, 1 times 1 plus 3 times 0 is 1. 0 times 1 is 0, minus 2 times 0 is 0. And m times j is 1, 3, 0, minus 2, 0, 1, which is 1 times 0 plus 3 times 1, 3, 0 times 0, minus 2. So what does this mean for our matrix transformation? Here's I, here's j, and here's a vector a, AB. That means it's a times I plus b times j. Now, if we go over to our range, our codomain, this is our domain, this is our codomain. M times I goes to 1, 0. That's actually just I again. So here's m times I, and then m times j goes to 3 minus 2. 1, 2, 3, 2. This is m times j. So our vector a times I plus b times j is going to go to a times m1 plus b, a times m times I, which is this vector. We'd stretch this out by a times mi, and then we take b times mj, that might be, and then we add those together to get the resulting vector. So I can break down the matrix multiplication into just what happens to the basis vectors, and then I know what happens to every other vector because every other vector is just a linear combination of the basis vectors. And you just use the same coefficients, you just multiply by the images of the basis vectors. So if we think about a 2 by 2 matrix with any kind of numbers, what's that times 1, 0? Well, a11 times 1 plus a12 times 0 is a11. a21 times 1 plus a22 times 0 is a22. So the first column is where I gets mapped to. If this is our matrix M, multiply this out, you get a11 times 0, a12 times 1 is a12, a21 times 0, a22 times 1. That's M times J. So that's the second column. So the two columns tell us where I and j go. And then any vector, m times ab, is always going to be A times Mi. That's the first column of the matrix, plus B times Mj. That's the second column of the matrix. So the codomain and the range. Codomain. Codomain is the set of possible outcomes. The image, also called the range, is the actual outcomes. And the classic example is the function from the reals to the reals defined by f of x equals x squared. And you know what the graph of that looks like. It's like this. This is the domain. The y-axis is the codomain, right? We said that the outcomes of this function are real numbers. Is every real number an outcome? And the answer is no. The range of the image is just the positive real numbers and 0, right? And if you remember back in 112, this is not an onto function. It's not onto the entire codomain, but it does have an image, and that's the values that you get here. So M is 130 minus 2. And if V equals K1, K2, is in domain, then M times V is K1 times Mi, which is the first column, plus K2 times the second column. This is M times I, this is M times J. So these two vectors are linearly independent. So the span of the two right? If you think of these as linearly independent vectors, they point in different directions. So the span of that is the entire codomain. Right? And so therefore this image, which vectors in the space are actually images of vectors from the domain? Well, that's the entire codomain. What happens if they're not linearly independent? So suppose we have a matrix A11, A12, A21, A22 equals M, and A11, A21 is where I goes to, and A12, A22 is where J goes to, and we'll assume they're not linearly independent. So that what means is in our domain, we have I and we have J. Multiplication by M. These are linearly dependent. Then they point in the same direction. So I gets mapped to this vector, and J gets mapped to this other vector. So what's the span of these two? Well, the span of these two is just this line. And that's the image of this map. It takes the entire plane and it maps it down onto this one line. So here the image does not equal the codomain, because the codomain is all 2 by 2, all vectors. And this is actually going to lose a dimension because it maps I and j, which is the basis, which are linearly dependent in the domain, onto linearly dependent, I and j are linearly independent in the domain, but they get mapped onto the same antimultiples of each other in the codomain, which means that it'll collapse the entire plane onto that one line. And so the image, which is that one line, is not equal to the codomain. And if you remember the terminology, that means this function is not onto. It's also not one-to-one either. So M is the matrix below. What is the image? What are vectors that if I multiply this by, I get as outputs? So if V is taken to be K1, K2, then M times V equals M times K1I plus K2J as my vector, my basis vectors, which is K1 M times I plus K2 M times J. So MV is M sub I is the first column. So K1 times 2 minus 3 plus K2 MJ is the second column, minus 10 times 15. And we can actually see here, because I set it up this way, that I can factor out a minus 5 out of the second one, and we get the same vector. So no matter what vector I pick, the image, this is in the domain, the image in the codomain is going to be a multiple of 2 minus 3. So if we think about what this matrix does, I have a vector I and a vector j and a vector K1I, K1I plus K2J. Remember, the K1 is the coordinate along the I-axis, the K2 is the coordinate along the J-axis, and it gets mapped over to this thing. So here's my domain, here's my codomain. I gets mapped to 2 minus 3. So there's M times I, and J gets mapped to minus 10, 15, which is in the opposite direction, but out here somewhere. So this is M times J, this is M times I. So where does this vector go? It goes K1 units. Its coefficient is going to be K1 times M1, K1 in that direction, and then K2 units in this direction, whatever that might be. So the vector that we get is just along this line. So my image is the span of the vector 2 minus 3, which is a line and one-dimensional. The codomain is all two-dimensional vectors, right? But our codomain is just our image is just a subset of that. Okay. So 3 dimensions. Here's a matrix below. What's the geometry of this function? So same kind of setup. In 3 dimensions, we have a vector I, J, and K that point in the X direction, Y direction, Z direction, and a vector B, which we'll call K1, K2, K3, any vector can be rewritten as K1 times I plus K2 times J plus K3, I guess K was not the best choice, times K, right? So we go K1 units in the I direction, K2 units in the J direction, K3 units in the Z direction to get to the tip of our vector. So what does M times V equal to? Well, that's M times K1I plus K2J plus K3K equals K1 M times I plus K2 M times J plus K3 M times K. So what this does then is we pick our vector, K1, K2, K3, and it's got coefficients. K1 goes with I, K2 goes with J, K3 goes with K. We take the matrix M, we figure out where M times I is, what M times J is, what M times K is. And then we use the same coefficients, K1 times MI plus K2 times MJ plus K3 times MK. The matrix transforms the basis, but the vector relative to the transform basis is the same as it is to the original basis. So what's M times I? 1, 0, 1, 1, 1, 1, 0, 0, 2 times 1, 0, 0. Remember that in 3 dimensions, I is going to have 3 components. If we multiply that out, you get 1 times 1 plus 0 times 0. Oh, you get 1 times 1 plus 1 times 0 plus 0 times 0. So that's a 1. 0 times 1 plus 1 times 0 plus 0 times 0. That's a 0. So that's the middle row times this vector. And then we take the bottom row times this vector. But this is just going to pick off the thing in the first column. So the first column is M times I. And you can do a similar thing to show that M times J is going to be the middle column, 1, and M times K is going to be the third column. So if I take, say, a vector B equals 1, 2, minus 1, right? I can rewrite that as I plus 2J minus K. So what's M times V going to be? It's going to be 1 times the image of I times this vector, 1, 0, 1, plus 2 times the image of J, 1, 1, 1, minus 1 times the image of K, 0, 0, 2. So in this picture, I is this red vector, that's my x-axis. J is this green vector, and K, is the vector along the green line, and K is a vector along the blue line. So it's I, J, K in the domain. M times I is this red vector. M times J is this green vector. M times K is this blue vector. So if I take the vector that's 1, 2, minus 1, so 1, and then we go 2, and then down to minus 1. So if I take this vector, that's 1, 2, minus 1, where is it going to get mapped to? It'll get mapped to one of these plus 2 of these. And where would that end up? It'll be up here somewhere. Minus 2 of those. And so that'll take us down a bit. Which is a terrible drawing. But we end up down here somewhere. So what happens with a matrix transformation is you start with the basis, I, J, K. It gets mapped to 3 other vectors, in this case, the red vector, the green vector, and the blue vector. And then any matrix that's a linear combination of I, J, K gets mapped to a linear combination of the images of I, J, and K with the same coefficients. And those images are, in fact, the columns of the matrix. So again, this, if I have a vector B equals K1, K2, K3, the matrix times V is going to be K1 times the first vector plus K2 times the second vector plus K3 times the third vector. Right? And keep in mind that this is M times I. The second column is M times J. The third column is N times K. Those are my three basis vectors. And this vector can be rewritten as K1 times I plus K2 times J plus K3 times K. Okay, but there's a thing here, right? If we notice this vector minus this vector gives me the third vector. So this can be rewritten as, so this last vector can be rewritten as 1, 0, 1 minus 1, 1, 1. The columns are linearly dependent. Okay, so what does that tell me then? The image has lost a dimension, right? We started with 3 linearly independent vectors, I, J, and K, and we ended up with only 2 linearly independent vectors, 1, 0, 1 and 1, 1, 1. So the image is just the span of the 2 vectors, 1, 0, 1 and 1, 1, 1. And that's not equal to the codomain. The codomain is all possible 3-dimensional vectors, but we only got 2 dimensions. So if we go and look at this here, these 3 vectors are M times I, M times J, and M times K. So 1, 0, 1. Let's see. 1, 0, 1. This one is M times I. And M times J is this one. And M times K is that one. And all 3 vectors lie in the same plane, this blue shaded thing. So if I take any vector that's got in 3 dimensions and I multiply it by this matrix, what I'll get is I'll just get other vectors in this plane, in this nice 2-dimensional space. But the codomain, which is what we're looking at here, has all these vectors that are not in the plane. Any vector that's not in the plane is not in the image of our map. So what we've done then is the linear dependence of the columns meant that we lost a dimension. We've taken our 3-dimensional domain and we switched it into a 2-dimensional plane. So what about this vector? What happens if we don't have square vectors? So we need to figure out what's the domain and what's the codomain. So this is a 3 rows by 2 columns. So it can be multiplied by 2 by 1 2-dimensional vectors, and it gives us 3-dimensional vectors. Great, so our domain is got a basis I and J. M times I equals 1, 0, 1. M times J equals 0, 1, 1. So if I pick any vector in 2 dimensions, call it K1, K2. Then M times K1, K2, keep in mind that this can be rewritten as K1 times I plus K2 times J. So M times K1 times I plus K2 times J equals K1 M times I plus K2 M times J. And that's going to be K1 101 plus K2 011. So the image is all linear combinations of the columns of the matrix, which is these two. And so if we try and draw this in 3 dimensions, which is not going to work very well because I'm really bad at drawing 3 dimensions. This is my x-axis, y-axis, z-axis. So 101 is 1 unit this way and then 1 unit up. So there's M times I, and 0, 1, 1, M times J is up there. And so these vectors span a plane in 3 dimensions. Hard to draw a plane. And so every vector here gets carried into a vector in the plane determined by these 2 vectors in 3 dimensions. So the image is not the same as the codomain here, but not because the columns were literally dependent, just because we didn't have enough columns. So codomain does not equal image. We started with 2 dimensions, and we took 2 dimensions, and we put them into 3 dimensions, but we didn't have an extra column in our matrix, so we couldn't expand it out to 3 dimensions. So what about this one? So this is a 3 by 2 matrix. No, 2 rows by 3. So what's the domain of this as a function? What's its codomain? Well, 2 by 3 matrix can be multiplied by a 3 by 1 vector to give us a 2 by 1 vector. So the domain is 3-dimensional vectors, and the codomain is 2-dimensional vectors. And you can see there's going to be a problem, right? We have to lose at least 1 dimension. If we're starting in 3 dimensions and going down to 2 dimensions, we have to lose 3 dimensions. We have to lose a dimension. And you can see by the shape of this that if we solve this, you'd end up with a parameter. So M times I is 1, 2. M times J is 1, 0. And M times K is going to be 0, minus 1. So if we think about this in terms of 3 dimensions, this is our domain. We're starting with I, J, and K in 3 dimensions. And the function is actually going to map them down to 2 dimensions. Mi goes to 1, 2. Mj goes to 1, 0. And Mk goes to 0, minus 1. So any vector I pick in here is going to get mapped down into the plane. You can see that these 3 vectors, any 2 of them are linearly independent because they don't point in the same direction, but all 3 are linearly independent. And in fact, Mi is equal to Mj minus 2 Mk, or 1, 2 equals 1, 0 minus 2 times 0, minus 1. So here the codomain equals the image. But we did lose a dimension in going from 3 dimensions to 2 dimensions, right? We had to take our I vector and stuff it into a plane that already contains the K and J vectors. So columns are the images of the basis. Linear independence means that we lose a dimension somewhere. So we lost a dimension here because those are linearly dependent. These were linearly independent. We started with 2 dimensions. We kept 2 dimensions. These are linearly dependent. We started with 3 dimensions, but we ended up with an image that only had 2 dimensions. These were linearly independent. So we started with 3 dimensions and the map kept all 3 dimensions. So generally in higher dimensions, if we have an n by m matrix, oops. If this is n by m, the domain would be m by 1 vectors, so that's m dimensional ones B, my matrix M, and my output W is going to be an n by 1 matrix. The dimensions, right, tell us something about what the possibilities are. If we start with more dimensions than if m is bigger than n, if we're going from a big space down to a small space, we're going to have to lose a bunch of dimensions. And that's, you know, if you have more columns than rows, right, you're going to lose some of your if you have more columns than rows, then your column vectors are linearly dependent, and so the span of them will be smaller than what you started with. So if I have a matrix M with n rows and m columns, so domain is n dimensional. I don't know why I call them n by m. They should all be m by n. I don't know why I reversed the n's in the m's. So they're n dimensional vectors. And so the basis for this is the vector they're usually called E. E1 is 1, 0, dot, 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 0. E2 is 0, 1, 0, dot, dot, dot. And E3 is 0, 0, 1, dot, 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 dot. So what's, if my matrix is A11, A12, out to A1M, we have M columns, and A21, A22, dot, 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 A2M. The first number is the row number, the second number is the column number, AN2, dot, 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 ANM, dot, 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 times E1, which is 1, 0, dot, 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 0. That's going to give you just the first column, A11, A21, like we saw above, AN1, etc. So M times E2 equals the second column. And M times E to the n, for example, E sub n would be the nth column. Let's see, M, oh, did I get this backwards? M columns. First row, second column. So I want to multiply this by things of dimension m. Oh, fudge. So this should be m dimensional vectors. Okay. And what do we know about vectors? Every vector is a linear combination of the vectors in the domain. A matrix times a vector is the same coefficients, but the matrix, because it's linear, can just go through and multiply the vector. And then this thing here, ME1, that's the first column, plus K2 times the second column, plus dot dot dot, plus Km times the mth column. And here we're interpreting these as vectors in the codomain. And so the image of the map is whatever vectors in the codomain can be expressed as linear combinations of the columns of the matrix.